Okay. Well, let's keep on keeping on here with chapter 1. So, last section we talked about conditional probability. So today we're going to flip gears slightly. We're going to talk about, well, not really flip gears. We're just going to talk about when the given information really doesn't tell you anything. And that's the idea behind, ooh, hey, why is that so, that's the laser pointer still on apparently. That's the idea behind independent events. So that's what we're going to talk about today. So one of the bigger money makers in casinos happened when they decided to put up a board at the roulette wheel. If you're not familiar with roulette has different slots with numbers 1 through 36. Those are red or black. There's 18 reds, 18 blacks. They also have green ones that are 0, double 0, and now apparently they've also added a 000 and for roulette in Vegas for some of the casinos. Anyway, of course, the wheel has absolutely no memory of what's going on, right? It's just as likely to land on a 1. If it landed on a 1, it's just as likely to land on a 1 again as anything else. But what the casinos did was they put up a board at the roulette tables where it shows the last, say, 10 outcomes of the roulette game. So every once in a while, you get a string of, 7, 8, 9 black numbers go up in a row. And of course, gamblers like, oh, it's got to come up red next time. Because it's been black 9 times in a row. Well, again, the wheel doesn't remember what it's done the last 8 times, right? So gamblers thinking they have given information is going to make it more likely for something to happen when it just doesn't happen, right? So that's the idea behind independent events. Having knowledge about one event does not change the probability of the other event at all, right? So as a definition, we say events A and B are independent if the probability of A is the same thing as the probability of A given B, and the other way around, okay? Oops. Probability of B is the same thing as the probability of B given A. The fact that you were given any information at all about A and B doesn't tell you anything, right? It didn't give you any added information. The probability stayed the same. So as an example, if you roll a die, what's the probability of getting a 6 on the second roll given you got a 6 on the first roll? Well, it's still 1/6 because the die doesn't remember what you rolled in the first roll, right? Okay. So that's the idea behind independent. Now, of course, if we remember how we calculate our, if we remember how to calculate our conditional probabilities, remember our conditional probabilities are computed by doing the probability of the intersection over the probability of the given, right? We can rearrange that. Well, we'll rearrange it and use the fact that they're independent. If they're independent, then we have the probability of A is probability of A intersect B over probability of B. And we can clear the fraction and get that our probability of the intersection is the product of the probabilities. So this is an alternative way to define independence. As say the probability of the intersection of the two events is the product of the two probabilities. This might even be a better way to define independence because remember with your conditional probabilities, you had to worry about the denominator being 0, right? This works no matter if one of them is 0. So this is probably the property that we're going to use most often when we're doing independent events to help us calculate some things. So this is the big thing for this particular section is, can we use this formula appropriately? Okay. All right. So some other examples of when things are independent versus when they're not. We've talked about drawing something with replacement versus without replacement. If it's with replacement, what we mean is maybe we're drawing out balls out of an urn, because that's what probability problems like to say, are balls out of urns for some reason. Pick it up, record what ball you got, throw it back in there again, mix it back up, you still have the same chance of picking that same ball again, right? Versus without replacement, if I pick a ball and keep it out, now I've changed the probability of what's left or what's on the second draw, right? So drawing with replacement is independent. Drawing without replacement is not. Now, if what you're drawing from is large enough, you might as well assume that they are independent of each other. What I mean by that is, if you take people from a population, certainly it's a finite population, but if you've got hundreds of millions of people that you could draw from, choosing two people without replacement is basically the same probability, right? You haven't changed it much. Okay. So you'll see things when you're doing drawing things, even without replacement, if the thing you're drawing from is big enough and your sample size is small in comparison, you treat it like it's independent anyway. And we'll see what I mean by that later on as we investigate particular probability distributions. All right. Our goal for today, though, is just to play around with this independence property. So let's look at this first example on the sheet that I gave you here. So it tells you that if the probability of A is 0.8, probability of B is 0.5, and the probability of the union is 0.9, can you determine whether or not they are independent? Well, again, they're independent if the probability of the intersection is equal to the product of the probabilities of the individual events. Okay? So what do you think we should do to start this off, do you think? Split up the union, right? Yeah, okay, good. How can we rewrite probability of the union? Good. Sum of the probabilities minus their intersection, right? So do we have enough information here to figure out what the probability of the intersection is? Yeah. Probability of the union is 0.9. Probability of A is 0.8. Probability of B is 0.5. And what do we get? Probability of A intersect B is 0.4. Looks like if I solve for that. So now we're close to having enough information here to determine whether or not they're independent. If they're independent, what else do we need to see is equal to 0.4?
The product of probabilities of A and B.
Good, the product of the probabilities of A and B, right? Okay. So if I do the product of the probabilities, oops, I forgot to write both of them in there. Sorry about that. I'd have 0.8 times 0.5, and we get 0.4 again. And these two things are equal, right? These are equal to each other. So A and B are independent. So again, using our union formula and then the definition, or at least the alternate definition, I suppose, of independence, we can figure out whether or not they're independent. Is that okay? All right, well, let's look at the next one. This one's got some decent stuff in it because it's got a few of the words that we talked about and properties. So we know that A and B are independent. We know B and C are mutually exclusive. And notice in what you're trying to figure out the probability of, there's also a complement in there. Right? Okay. So Pardon me, goodness. All right, so let's see how we would do this first. Well, what do you think we might want to do first here? Okay. So we can certainly figure out what the probability of the intersection of A and B is, right? Since they're independent, we can just do what?
1/4 times 6.
Good. Since they're independent, we can break up the probability as a multiplication. Generally speaking, by the way, we've already been doing that, right? Breaking up our and probabilities as multiplication because we can think about doing task 1 and then task 2. We had to be careful in some of our problems. Did the, say, denominator change as if you're pulling without replacement? Right? You've had problems like those. But in this case, we can just break up that and probability as multiplication since they're independent, and I can multiply those two things together and get a 24th. So that's one piece of information we might want to know. What might you want to do next? Yeah, split the union up like we did in the previous problem, right? How can you rewrite that probability of the union?
Probability of the A intersect B complement plus probability of C, then minus the intersection.
Okay. Yep. Two of those pieces we know, right? What is the probability of A intersect B complement?
1/3.
Yeah, 23 over 24, good. And probability of C is a half. Yep. Okay. All right. The last part we still need to work on. So we still need the probability of that intersection, don't we? Intersection of A intersect B complement and then intersect C. How might we attack that? Say it again. Well, in order to be able to multiply the 23 over 24 by the 1/2, what would I have to know about the two events? They have to be independent of each other, right? Don't know if I know that yet or not, right? We have to know that they are independent. If they are independent, then we can. Absolutely. Okay. It's a good thought. Absolutely. So how would we determine whether or not they're independent or if there's another way to go about it? Well, let's think about it a different way. Let's think about a picture here, maybe. So if I want to draw a Venn diagram, let's get the intersections to work, or the overlaps to work. If I put A in and I put B in, certainly they have some overlap, right? But how would I draw in C?
No overlap.
No overlap with B, right? Why would I have no overlap with B? They're mutually exclusive, correct? All right, so let's think about what set we've got here. This says do the complement of A intersect B and then intersect that with C. Well, what's representing the complement of A intersect B in my picture?
Everything not in the overlap.
Yeah, everything that's not in the overlap, right? So all this stuff out here, all this stuff out here, up to the overlap, right? Up to the overlap, and then, oops, it went right through the overlap, sorry. And then everything else. And then what do we want to do with that? Intersect it with C, right? Yeah, Kevin. That's the complement of A intersect B. Yep. Intersect C. There's C. What region am I looking for? C, right? That intersection is just C, isn't it? Yeah. So this is 23 over 24 plus a half, and then minus just the probability of C, because that's what the intersection is in this case. But 1/2 was the probability of C, wasn't it? So we just end up with 23 over 24 when we're done. Okay. Questions on that at all? Another way, I drew the picture, but another way you could have done this was using some set properties. Just to do this off to the side real quick. You don't have to write this down if you don't want to, but A intersect B complement using De Morgan's laws. Remember, the complement of an intersection is the union of the complements. And then if I take this and intersect it with C, this situation has what looks like kind of a distributive property. This is it's A complement intersect C union B complement intersect C. Basically, we're distributing the intersection over a union. If you're familiar with the set theory properties, I like the picture better because it was really quick, right? Okay. What do we know about B and C? They're mutually exclusive, correct? So that means that C is included in the complement. So this part right here simplifies to C because B intersect C is empty. So C has to be in the entire complement of B. So this just simplifies to C. This is contained in C because it's an intersection of C with something else. So when you do the union, you just end up with C. We're using subset properties here, right? C is a subset of B complement, so the intersection is just C, which is what we did from the picture, isn't it? Essentially. Okay. And then this is a subset of C because everything in here is contained in C. So when I union with C, I didn't change it at all. So I end up with C. So you could have also seen that simplified to that if you would have gone through set theory properties or set properties. Since I wasn't in a discrete math class, I wasn't as worried about doing all the set properties. Okay. But if you've had discrete, you've probably played around with these things. If you haven't had discrete and are going to take discrete, you'll see those things as well. My question is are you okay with the picture? This picture okay? Picture's good. All right, good. Any other questions on that one at all? All right. Let me tell you what the definition of mutually independent is, and I'm going to let you work on this problem for a minute. Mutually independent events says that you have all sorts of intersections that you can split up over multiplication. So when you're mutually independent, this means that the probability of A intersect B is the product of the probabilities A intersects C is the product of the probabilities. B intersects C is the product of the probabilities. And if I do the product of all, or I do the intersection of all three, it breaks up over as a product. You might think that, okay, so the first three conditions are actually referred to as pairwise independent. If you take any pair, they're independent. The mutually independent also requires this probability of the intersection of all three to break up over products as well. They give you a nice example in the book of why there's a difference between the two. So say you roll a die twice, and your events are odd on the first roll, odd on the second roll. Those are clearly independent, aren't they? Right? Odd on the first roll and odd on the second roll are clearly independent. Your third event is the sum is odd. That is independent of the other two. The reason why it's independent of the other two is because if you roll an odd on the first one, well, you have even, basically half even, half odd for the second one, right? And it's going to make the probabilities break up appropriately. Unfortunately, the product of the intersections is 0 of all three, because you cannot roll an odd on the first and on the second and get an odd as sum, because odd plus odd is even, right? So the probability of the intersection of all three would be 0, but the product of the probabilities would not. Because certainly you can roll an odd on the first, you can roll an odd on the second, and you can get an odd sum independently, right? So that's an example of something that where the events are pairwise independent, but the intersection of all three is not the product of the probabilities. Okay. So like I said, make sure that you understand what mutually independent means versus pairwise independent. We'll see another example in a minute of this as well. But see if you can use those facts that I just wrote down to solve that particular problem. Work on that one for a minute. Union in this case. Okay. Minus which part?
The intersection.
We got
of all three.
I got a little bit more than that though, right? Because we got some middle pieces, right? What do we get? Yeah, we got to do all the pairs intersections, right? And then what we add back?
The intersection of
All three. Good. Great. Yeah, so we're using that probability of the union of all three being able to be the probability of the sum of each individually minus the pairwise intersections, and then add back the intersection of all three. Now notice they tell you that A, B, and C are mutually independent, and we're given complements here, right? All right. So it is actually a theorem, which we haven't talked about quite yet, but it is a theorem that if, I'll write this off to the side here, if A and B are independent, then so are A complement in B, A and B complement, and the complements of both. So if you know the individual events are independent of each other, then I can do the complement of one, not the other, still independent, or the complement of both, and they're still independent. They do the proof of the first one in the book. The other two are similar to what the proof of the first one is. So I'm not going to take the time to do it. It's in the book. I'm not going to make you reprove it. I might actually do one in the video too. I can't remember. It's been a while since I did the videos. So But in any event, since all of those pieces are independent, and we know things are mutually independent at this point, how can we write it? What do we know all of these things here? What's the probability of A complement? 0.5. Probability of B complement is 0.4. Probability of C complement is 0.9, right? Or just C. I'm sorry, it's not the complement. My apologies, just 0.1. What do we do with these two? Yep, take the probabilities of the complements individually and multiply them, right? So we'll do, this one will be 0.5 times 0.4. The next one will be 0.5 times 0.1. The next one will be 0.4 times 0.6. 0.6. 0.1. Sorry. Apparently I really want to mess up the probability of C. I don't know why. And the last one will be the product of the three. So 0.5 times 0.4 times 0.1 this time. Okay. Not too bad. Thrilled to death about it, I see. As usual. All right, let's look at the next one. This one, they're starting to give you some scenarios, easing us in here. You're going to throw 3 dice. Each event, E1, E2, E3, is rolling a 6. Just depends on what die you're looking at. Maybe you have 3 different colored dice. Maybe one's red, one's blue, one's green, and so you want a 6 on the red one, a 6 on the blue one, or a 6 on the green one. How do you think we'll attack this one? Same way, right? Do the exact same thing we did in the previous one. Sum up the individual probabilities. Subtract their the pairwise intersections. Oh my heavens. E3. And then add back the probability of the intersection of all 3. Again, I think it's pretty obvious that the events are pairwise independent, right? The roll of one die is not going to affect the roll of any other die. And then they need to be mutually independent in this case. But again, it doesn't matter what 2 of them are doing. It has absolutely no effect on the third one. So that's the mutually independent, right? That no matter what is happening on any 2, it doesn't affect the third one. Notice that's different than the example I gave you before of roll an odd on the first die, roll an odd on the second die, do a sum that's odd on the, right? That's a third event. That's definitely kind of depends on what happened with 2 of them, right? That's why you can see that they're not mutually independent, even though they might be pairwise independent. That's the idea. All right. Since they're all mutually independent, we can do all of these probabilities by multiplication, the intersections, and all of the probabilities are going to be what in this case? 1/6, right? So we'll have 1/6 plus 1/6 plus 1/6 minus a 6th squared for each of the other ones, and then plus a 6th cubed. It's a 6-sided die, and you're rolling a 6. Okay. I guess they probably should have told you it was a six-sided die. That's the one you're usually you're used to, right? But if you do any type of role-playing games, you probably know more of more. A four-sided die. Oh. 4, 6, 8, 12, and 20 are the what are referred to as the platonic solids. They're the perfect ones, right? There's a four-sided die would be 4 equilateral triangles. A six-sided die is your normal die. It's 6 congruent squares. 8-sided again uses triangles. 12-sided uses pentagons, and 20-sided uses triangles again. Okay. And those are the only 5 that you can form using congruent of the same shape all the way around that are actually regular polygons. You can do congruent shapes, just not polygons. As for example, I think a 10-sided die has congruent shapes, but they're not regular polygons. Triangles, squares. Regular means they all have the same length of sides. All right, anyway. Is that okay? Yeah, on a tangent there. But it's math class, it's okay. I'm allowed to go off on a tangent, right? All right, so here's an example where you've got 3 events. They're pairwise, but not mutually independent. So think about this one for a minute or two. See if you can calculate the probability that none occur. And then we'll chat about it. And then I want to compare this to the previous one when we're done. So work on that one for a minute or two. That's just a second ago. Ask what were we trying to find in this previous example? So it says the E sub I says denote the event that the ith die results in a 6, and we're doing the probability of a union of these 3. Well, again, in English terms, we think of union as what word? Union is or, right? So this is the first die is a 6, or the second one, or the third one, right? Is what that says. So said maybe a little bit better, that's the probability of rolling at least 1. Yeah, exactly. At least 1 6, right? Is what that's saying. Okay? So this is the probability of rolling at least 1. Pardon me. Goodness. Notice that involved a little bit more work to do it that way, right? Another way you might have thought about doing this is, what's the complement of doing at least 1? None, right? You could have done the complement and subtracted it from 1. Notice none of them would mean not a 6 and not a 6 and not a 6. You could have just multiplied 3, 5, 6 together and subtracted it from 1 in that case, right? You could have also done it that way. Okay. Why did I bring that up for this next problem? Because so basically this is the complement of at least 1, isn't it? It says the probability that none of them occur, right? So you want not A and not B and not C, right? Agree? This is the probability that none of them occur. That's the complement of not A. That'd be not A, because that's A didn't occur, and B didn't occur, and C didn't occur. All right, it's that complement idea. It's the complement of the union. So what we're looking for is probability of A complement intersect B complement intersect C complement. The problem is, what do they tell us in the problem? They're only pairwise independent. They're not mutually independent. So is this the same thing as this? No. Okay. So I really do need to attack it from the complement idea, right? Okay. So this piece right here, this A complement intersect B complement intersect C complement, is the complement of the union. The complement of at least 1 is none, right? This union idea is that A occurred, or B occurred, or C occurred. This is at least one. This is none. They're complements of each other, right? Now we should be able to compute the probability of the complement just like we did in the previous problem. We can break up the union just like we did in the previous problem. Right? Do the individual probabilities, subtract off the pairwise intersection probabilities, and add back the probability of the intersection of all three. Right? This looks a lot like the previous problem, didn't it? Okay. All right. Do we know all of these things now? Can we, or at least can we figure them out? Yeah. It says each event has a probability of a third. How do we figure out the pairwise probabilities? Multiply them. Good, because it says they're pairwise independent. And since each has a probability of a third, I can just do a third squared, right? Yes. Say that again. I'm going to do that at the end. I'm going to do it at the end. I need to find the probability, and then I'm going to do 1 minus that. Yeah. That's why I didn't put it on there. That last probability we're not going to calculate through a product because it tells us it's not mutually independent, but they give us that probability is 1/10. Yeah. So what is that? 3 and 13/30ths? Did I do that right? No, wait, that's that. Sorry, say it again. 23. I forgot to double the other one. I did a third plus a tenth instead of 2/3. Sorry, 23/30ths for that one. So then the probability of the complement then will be 7/30ths when you're done. No one okay? Yeah. Do you have a question, Matt?
Yeah, would you be able to do the same thing, like all the complements individually? That's what I tried to do, but then I got stuck again.
You can do the complements individually, except that I can't do the product here because I don't know that they're mutually independent. That's the issue with that one. So I have to attack it using the original. Yeah. If you knew they were mutually independent, then you could absolutely do it the other way. The problem is that I didn't know that I could do this. And the only formula we have for rewriting is with a union. So I needed to convert it to a union problem and then rewrite it that way. Is that okay? All right. Do another one here. This one just wants to compare calculating something with independence versus mutually exclusive. It's just a matter of making sure we remember what the definitions mean. But in both cases, how do you think we want to attack it? What do you think we want to do first, no matter which of the cases that we're doing? What piece do you think you might want to rewrite first? Split up the union, right? Because remember, our formula that we use for calculating the probability of the union involves a probability of the intersection. And notice, independent and mutually exclusive both says something about the probability of the intersection, right? Independent says what you can do what with the probabilities? Multiply them. Mutually exclusive tells you what about the probability of the intersection? It's 0, right? So in either case, we want to rewrite the union probability involving the intersection so that we can use whichever scenario we have. So if I do the probability of A union B, we've done this about 5 times today at least. Probability of the union is the sum of the probabilities minus the probability of the intersection. Using actuary 1's assumption, what's your equation going to look like?
PA plus PB minus PA times.
Okay. And then what values can you plug in from there?
PA is 0.5 and the union is 0.7.
Okay. They tell you the union probability is 0.7 and A's probability is 0.5. Can you figure out B's probability from that? It's just an algebra problem at this point, right? Subtract your 0.5 over and multiply by 2. So you get 0.4. Yep. Based on actuary 2's assumption, what does your equation become?
Union equals PA plus PB.
Good. Actuary 2's assumption is that they're mutually exclusive, so the probability of the intersection is 0. Right? So now we can, again, solve for probability of B pretty quickly and get 0.2, it looks like. The problem asks for the absolute difference between the two. It just means do the biggest bigger minus the smaller, so you get 0.2 in that case. Yes.
Mutually exclusive.
So mutually exclusive means the intersection is empty. And so the probability has to be 0. That's what mutually exclusive means. So it can't happen at the same time. Okay. You think we got independence pretty good? Or do you want to see it? Yeah, Declan.
Can I see what we did for actuary?
Yeah. Yeah. Okay. Think we're okay, or do you want to see another? Okay. Or do you want to see another one, or do you think we're okay? And go on to some other stuff. You tell me. You all seem bored, so that's what I'm asking. All right. So the next thing we're going to talk about, which will finish up chapter 1 here, is Bayes' theorem. So that's more problems. What's that? So we did an example of Bayes' theorem the other day when we did conditional probability, that last conditional probability example that we did that everybody was so happy about. All right, so let me flip over here. All right. So the idea behind Bayes' theorem, let's go through this example that we have and then talk about what the idea of Bayes' theorem is and then do some more examples with it. I don't ever actually write down the theorem very often. I just go through and know what I need to do with these problems. So let's talk about how I know what to do with these problems. So hopefully we can get to that same comfort level. All right, so we've got, it says 10% of employees in their first 5 years earn 100,000 or more. 20% past their 5 years earn 100,000 or more. And then it says overall 13% earn 100,000 or more. And it wants us to determine the proportion of employees that were in their first 5 years. So these first two pieces of information here, this one here, and this one here, are basically telling you conditional probabilities. Given some information, it's giving you a probability that something happened. Okay? I've got two events there. I've got employees in their first 5 years. I've got employees earning 100,000 or more. Right? And then I have the complement below that for the one of them. But do you see where there's a conditional probability in there? Right? I've got employees in their first 5 years. I know I'm in that subset, right? I'm in the group of employees who are in their first 5 years. If I'm in that subset, 10% of those in that subset earn 100,000 or more, right? So I know that the probability of earning 100,000 plus given in the first 5 years is 0.1. That's what that conditional probability is, right? What's the second sentence say in a probability statement?
The same thing except after.
Okay, yeah, it's literally the same thing except that it's the complement of that set, isn't it? Oops. Agree with that? Now notice the third sentence is not a conditional probability. It just says overall 13% earned, right? Right. Pardon me. So these conditional statements, remember how we calculate conditional probability. This first one how do you calculate conditional again? What do you do? Yeah, the intersection, right? Over what? Okay, good. Agree with that? And it's the similar thing for the second one, correct? We just changed it to past 5 years for each of those two things. Okay. All right. Pardon me. Well, we know this number. They tell us this one, right? This is what we're trying to find. We need to figure out what that piece is, don't we? Okay. If we can figure out that top piece, then we should be able to get the answer that we want just by solving, right? So let's look at that top piece. And this is about basically what Bayes' theorem is all about. Let's go back to our conditional probability formula again. I'm going to do this off to the side and then I'll rewrite it. That's this, right? You agree? But remember that we can also rewrite this, well, if I multiply, I should say, you get your probability of A intersect B looks like this, right? Oops. Like that. But notice that you could also do the exact same thing if you flip-flop your A and B around, can't you? If I make this probability of B given A, notice your top is still A intersect B, correct? Just the denominator changes, doesn't it? I personally, my brain likes to think about this. I know it's a vertical bar, but my brain likes to think about it as a fraction because it looks like these cancel. So I keep them straight. My brain is weird, but I'm a mathematician, of course it is. All mathematicians have a screw loose. It's just a matter of how loose is the screw. Okay. Mine's just a little more loose than others. It's fine. Okay. All right. In any event, notice basically what we're doing here is this gives us kind of a bridge, right? These two things have to be equal to each other. So what this allows us to do is basically flip around the conditional information, right? It allows us to flip the conditional around. So up here on this top, let me scroll over a little bit. On the top here, I can flip the conditional from being first 5 years. I can flip that around to being, oops, what just happened? Why did you do that? I can flip that around to be, stop it. Okay, it's going to be a jerk today, apparently. I don't think I set it in the background, so I'm moving the page. That's part of my problem. There we go. Sorry, technical difficulty. Back up here again. All right. So you can flip around this top. Rather than the first 5 years being the conditional, you can make it be the conditional part being earn 100,000. Right? I can make that part be the conditional and then make it first 5 years given earn 100. I'm flipping it around. That's what this allows me to do, right? This says the intersection is the given probability of the given and then the conditional probability. This also says that same exact intersection is just the other way around. That's all I did was just flip it the other way around. Okay. All right. Why does that help? Well, it helps a little bit because I know this number, don't I? I still have a little bit of issue with this number. I don't know that one yet. Right? But I do know that first number. And we still know this number over here, don't we? So right now we've got, pardon me, this number over here was 0.1. This number up here is 0.13. Ooh, hey. And this is still where I'm trying to find. We agree with that? Okay. I still have issues because I still have two unknowns, don't I? I still don't know what this one is either. I'm not given that one. All right. Let's look at the other one, though. We haven't used this conditional probability, have we? First, let's rewrite the conditional. How would I rewrite that?
The intercept over P of past values.
Yeah? How do we flip it? How do we do the involve the other conditional? Right now, the given is past 5 years. I want to flip it around and make the other part the conditional. How would we rewrite it to make the other part the conditional?
P of 100,000 times probability of earning 100,000 given past five or backwards.
Backwards, yep. Past 5, given 100,000 over probability of past 5, right? You see what I mean by flip it around? The original given information was past 5 years. Now the given information is 100,000. We agree with that? Okay. Now we can plug in the different numbers. We've got 0.2. That was this probability over here. 0.13. Probability of past 5 given 100,000 over probability of past 5. Perhaps at first glance, it doesn't look like I did much. Didn't look like I helped, right? Kind of icky. Okay? However, I really do have the same two variables involved in both equations. What can I say about these two events? They're complements, right? So really it's the same variable. I just need to rewrite it, don't I? What about these two conditional events? Notice I have the same given. These are still complements, right? Okay. So rather than keep writing the same words over and over again, let's write this as 0.1 equals 0.13 probability of A given B over probability of A. And the other one is 0.2 equals 0.13 probability of A complement given B over probability of A complement. I just try to not have to write so many letters. Right, not to write so many words. Do we see how those are complements of each other? First 5 and past 5 are complements of each other, right? Right. So let's just rearrange the equations a little bit. Keep going off to the side. I'd have 0.1 probability of A equals 0.13 probability of A given B. The other is 0.2, 1 minus probability of A equals 0.13 times 1 minus the probability of A given B. They're complements of each other, so I can do 1 minus. I know I changed the word into a letter, but what am I trying to solve for? What's the problem asked us to solve for? The probability of in the first 5 years, which is what I labeled with A, right? Okay? I want probability of A, so do I care what this conditional probability is? No, I just want probability of A on this side, right? So if you can eliminate the probability of A given B over here, I can just solve the probability of A. What do I need to do with the two equations to eliminate that conditional probability? Add them. I've got the same coefficient on them, don't I? If I distribute the 0.13 through, I've got the same coefficient on both, right? So if I add the two equations together, you'll get 0.2 minus 0.1 probability of A should equal 0.13. Because those will, I just distributed the 0.2 through and added down. I did 2 steps at once, I know. And if I subtract, add, divide, I think you get probability of A will be 0.7. I know I did the algebra fast. You didn't like that?
Wait, where did the thing on the right go?
This part? This part?
One above.
The one above. So distribute your 0.13 through and then add down. You got a positive 0.13 conditional probability and a minus 0.13 conditional probability. I just eliminated the variable. If you like it better, make it an X and a Y. And I just eliminated the Y's. And kept the X's. I know, I did that. If you've got questions about the algebra, I'm happy to go through it. But we just distributed this through and then they have opposite signs. So when you add the equations, they cancel. I know I did it fast. We're going to do more of these as we go here. Got time for another one. But the whole point of this was the ability to be able to switch around the conditional on the top. Okay? That's the whole point of Bayes' theorem. Right? So do another one here. If I scroll over. Same idea here. We've got a blood test that indicates the presence of a disease when the disease is actually present. Given the test is positive, the probability that the disease is present is 50%. You have a 4% positive rate, and you want the percentage that has the disease. Okay. All right. So let's look at the first two sentences again. It says, indicates the presence of a disease when the disease is present. Do you see a conditional probability there? What's the given when the disease is present, right? So probability of positive given disease is 0.95. So the probability, it indicates the presence of the disease 95% of the time when the disease is present. Probability positive given disease is what we have there. What's the second sentence tell you? The flip of that, right? Given that you've tested positive, it tells you the probability that you actually have the disease. Probability of disease given positive is 0.5. Everybody okay with those flip arounds for the conditional? Third sentence is pretty easy, I hope. Probability of positive is 0.04. Okay. We're trying to figure out probability of disease, right? Agree? Okay. Pardon me. Notice that the first conditional, if we rewrite that using our conditional probability formula, how would you rewrite the first one?
Intersection of root P of disease.
Okay. Oops, I'll write it as an and. Over. What goes in the denominator? P of a disease. Good. Probability of the intersection over the probability of the given, right? The reason, that's why I started working with this one first, is because that was what we were trying to find, isn't it? We know this number. We're given that number, aren't we? So just like the previous problem, I need to work on that part. Agreed? Just like the previous part. Do you have a question, Kevin? Which part? This is what we're trying to find, right? Yeah, so it's this part here that we're trying to, I don't know that number yet. That's what I'm trying to find. This sentence is telling me that value. This sentence is telling me what I'm trying to find. The reason why I started with this particular conditional is because with that conditional, I can figure out that that was where that probability that I need to find comes up. Okay. All right. So quickly, since I got about a minute or less, I need to rewrite this and probability because I still don't know what it is. All right. But this is where we flip it around. The original given was disease, right? I want the given now to be positive. Right? And the reason why I know I'm flipping it this way is because my original given was disease. I want it flipped, right? So I want the given to be positive. The probability that goes out in front is the same probability. Do I know these two numbers now? Yeah, we're given both of those numbers. And now you can solve at that point. I'll let you solve for the last part, but you can solve it now, all right? So again, the idea behind this is just using our conditional, use this conditional probability to be able to flip-flop the conditional probability formula to be able to flip-flop the given with the whatever the given information is, in our formula. That's the idea. Right. We'll do more of these on Thursday. There should be a video about Bayes' theorem on Moodle as well. So if you want to watch that for Thursday, I'll give you a new assignment. I know you already got an assignment due on Thursday, so I'll wait to give you one over 1.4, and I'll do it at the same time as 1.5. Okay. All right. Have a good one. We'll see you on Thursday, if not before.